Welcome to ATMOS 5000 Day 38. We're looking at Chapter 9 from Stull, Section 9.3, trying to understand weather maps primarily. We'll be looking at the data that's plotted on the weather maps and trying to figure out how to interpret the station plot models. We'll talk about the basics of contouring analysis, and then we'll introduce a few of the map symbols that are used to denote fronts. So here in the upper part, we have a weather data station plot, which is depicting the weather at a given location. And the center basically identifies where the location is at. And then based upon that, we also have wind. So over here on the right, we have a wind bar that would normally be there. The reason it's circled is because that would be a situation where we have calm winds. The coloration in the middle of the dot kind of depicts the cloud coverage. This would be overcast. And then the upper left quadrant, the 34, is our temperature. The lower left quadrant, the 32, is our dew point temperature. And both of those are in degrees Fahrenheit because we're in the United States and we do it different than everybody else on the planet. The upper right-hand quadrant, where it says 168, is actually the pressure, but it's missing the first digit or the first two digits, depending upon whether or not it starts with a 9 or a 10. And it's in units of essentially tenths of a hectopascal. So that corresponds to 1016.8 hectopascals or 101.68 kilopascals. The number on the far left is the visibility, and that's in statute miles. The +1 is the pressure tendency over the last 3 hours, and then next to the pressure tendency is the glyph, which shows what the pressure has been doing over the last 3 hours. So that's kind of the basic idea, but there are other things that can be included on these, although more rarely. Other things that can be included are the types of high clouds, the types of mid clouds, the type of low clouds, the coverage from the low clouds, and the cloud base height. And that can also include information about current weather, about past weather, and about the precipitation in the last hour or the last few hours, depending. So just to recall back from the winds, if we have two concentric circles, that's going to be calm. A bar with no flags on it, basically, is 1 to 2 units, and for these it would be knots because that's the standard for wind measurement speed in the United States. Half a flag basically is 5 units. A full flag would be 10 knots, and then an actual flag that's filled in is 50, and you can add those together to get to whatever wind speed you want to get. So the sky coverage has many different types of symbols. There are basically 10 different symbols that could theoretically be in the center of that. And obviously an open circle is going to be clear and a full circle is going to be overcast. And then depending upon the coverage, it will increase. Essentially the black indicates cloud coverage, the white indicates clear. And you can see how the symbols that are used actually correspond to the METAR terms that we use in terms of sky, clear, few clouds, scattered clouds, broken clouds, overcast. And if there's fog and you can't really tell if there are any clouds at all, then you'll get this X, which means that the sky is obscured. It could also be obscured due to blowing snow, or it could be obscured due to blowing dust or other things like that as well. So the symbols for the barometric pressure tendency, basically this runs the gamut of everything that you can have, from steady rising to steady falling to everything in between, and it's just literally a graphical representation of the pressure trend over the last 3 hours. So these are the basic weather symbols. So we have the comma, which is the drizzle, the circle, which is the rain, the asterisk, which is the star, and then the triangles, which are various forms of ice, whether they be hail, graupel, or ice pellets. You can see the corresponding METAR code for DZ for drizzle, RA for rain, SN for snow, and GR for grapple, or GR for hail, and GS for grapple. Ice pellets, PL. And then we can put some of those weather symbols together. For example, if we put two solid circles, that would be light precipitation. If you had three solid circles, that would be moderate precipitation. If you had four, that would be heavy. You can also do other things like intermittent or virga, or things that are in the past hour but not now. But all of those can be done with snow, can be done with drizzle, can be done with rain. You can just basically identify whether it's light, moderate, or heavy, or intermittent. We also have different kinds of obscuration. We have 2 bars, which is mist, which is diffused fog with a visibility that's still greater than 5/8 of a statute mile, and fog is defined as visibility less than 5/8 of a statute mile. So, the fog has the FG, the mist is the BR. And then we have the infinity symbol is for haze. We have one that's specifically for smoke, and one that's actually used for smoke and volcanic ash, but would have different METAR codes on the right. And then we have sand, blowing dust, or sea spray along the way. And then we have different kinds of storms. And all of these are symbols that can be put in that left quadrant to indicate the current weather. So the most common one of these is the thunderstorm. It's a really cool little glyph. And it's basically got the updraft, the anvil, and the lightning coming out of the storm, and that's how we identify the thunderstorm. You can have lightning, but I've never seen the lightning symbol by itself. It's just always part of the thunderstorm glyph. I have seen the sandstorm and dust storm glyph associated with it. You never want to see the funnel cloud glyph. That would be bad. And superimposed upon these weather processes, you can put in slight, moderate, or heavy, depending upon what you want to do. So if you had a rain shower, that would be the downward directed triangle with a solid circle there. If you wanted to have a moderate shower, then you would basically, you could put in 2 or more of the rain symbols above the shower. You can have thunderstorm, and you can basically indicate the intensity by the number of things that are above it as well. And then we have different types of high clouds that could be shown, the different types of cirrus, different cirrostratus, cirrocumulus. We have mid-level clouds. And to be honest, I rarely see these, and I don't know most of these, and so that's something that I would have to look up if I saw these on a weather map. And then we have our low clouds. So we've got everything from cumulus humulus to cumulus meteorocris to cumulus congestus, all the way up to cumulonimbus down at the bottom with a thunderstorm, with an anvil top, glaciated ice. So over on the left is a more complete weather station model. So let's go through it real quick. Let's see, we have a temperature of 12.3 degrees Fahrenheit, a dew point of -4. We have a thunderstorm that's going on. The winds are from the northeast at 25 knots. We have a sky coverage that looks to be about 6/10. We have a visibility of 35 statute miles, and we have a pressure tendency of -2.8 hectopascals, and it initially rose but then decreased. In the past hour, we had a shower, and we have cumulonimbus clouds at the bottom, alto cumulus, and some form of cirrus on the top. The 3 next to the cumulonimbus glyph basically says that the fraction of low clouds is 3, category 3. And then at the bottom, we have 4. We have a cloud base height, which is category 4. And then we also have precipitation in the bottom right, where we have units of 1 hour, and we have 5 units, and the units in the United States are hundredths of an inch, so that's 5/100ths of an inch of rain in 1 hour. And back to the cumulonimbus glyph with the 3 and the 4, you really have to have a chart to be able to look up what the numbers 3 and 4 actually correspond to. So for the codes for the cloud base height, so we had a 4 on that, so that basically means that the cloud base height is between 1,000 and 2,000 feet AGL. So next we have contour analysis. And the whole idea behind drawing contours is that if you just have a map full of numbers, it's really hard to visualize where the high and the low quantities are and where the gradients are the greatest. So the contour analysis allows you to sort through that raw data and allows it to come alive so that you can actually start to focus in on the processes as opposed to just trying to look at the numbers themselves. So here is an analyzed weather map. So we have temperatures plotted here in terms of degrees Fahrenheit. And then superimposed upon that, we have isotherms, which are lines of constant temperature. And from this, it's easier to see that the warmest area is actually the southwestern US in Arizona. And the colder region is actually the Intermountain West in the Rockies, where the temperatures are less than 60 degrees. We also have warm areas in the Southwest as well. And then you can also tell where the temperatures are changing the fastest. So northern Arizona and northern New Mexico all the way up through Colorado and the upper Midwest have stronger temperature gradients than other locations. And it would have been hard to see that just looking at the numbers on the page itself. Another way to think about this is creating a two-dimensional representation of a three-dimensional atmosphere. So here, the analogy is a topographic map. So on the upper portion of this diagram, we have essentially a plateau or a long ridge with a cliff on one side. We have a broad valley in the bottom, and then we have a pointy peak on the right with ridges and valleys. And if we look at the topographic map associated with this, you can see the broad flat plateau where the gradients are really weak on the left-hand side of this topographic map, followed by the cliff, which is where all of the elevation lines are very close together, so you're rapidly changing elevation in a short distance. Then you have the broad flat plateau of the river valley, where there are almost no contour lines. And then as you come over towards the peak itself is identified by a circle. And then coming off of that, you have the ridges, and then you have the troughs. The troughs are the areas where the rivers or creeks would be flowing. And then the broad ridges are areas where you have higher elevations that stick out further away from the peak itself. And you can imagine the analogy here is if we're doing a constant pressure surface map and we have different heights of the pressure surfaces, you can see the direct analogy to the heights of the terrain versus the heights of the pressure surfaces. So the contouring analysis is really all about drawing lines of constant something or other, and that would be an isopleth. And there are lots of different isopleths that you could draw. You could draw lines of constant pressure, constant temperature, constant humidity. You could do constant wind speed. Basically, if there's any meteorological value, you could draw an isopleth for that value, and you could contour it on a spatial map. And the thing is that these isopleths, that every part along that line that you draw has the exact same value. So the other thing is that we often use the isopleths when we draw them between data points. We have to kind of interpolate So over on the left, we have, looks like temperature in degrees Fahrenheit. We've got 25, 31, 35 sort of thing, and we have a 30-degree isopleth. And clearly, somewhere between 25 degrees and 31 degrees has to be 30 degrees because the temperature is a continuous variable. And so when we're trying to decide where to draw that 30-degree isotherm, is it going likely to be closer to the 25 degree or the 31 degree? Well, obviously it's probably likely to be closer to the 31. So when we draw that isopleth between 25 and 31, we basically draw it closer to 31. And then, we've got a 25 and a 35 degree temperature. And so 30 would be halfway between those. So we're essentially doing kind of a linear interpolation when we're trying to draw the contours themselves. And over on the right, we have the contours of pressure in hectopascals. It's very common on lines on isobars, which are constant pressure, to have circles that will circle around the low pressure or circle completely around the high pressure. And we also have a 1004 contour. We're linearly interpolating between, say, the 1003.7 and the 1004.5, but it will pass directly through the data point that is 1004 hectopascals. So that contour line has to pass directly through the value that has the equal to what that contour line represents. So there are several rules for isopleths. The first rule is that they never ever cross. You can never have a 30-degree line cross a 35-degree line because that would imply that at one place at the intersection, the temperature is both 30 and 35 at the same time. So the other thing about isopleths is that they never branch or fork. You basically start an isopleth line, and the only way to end it is to either complete the circle where you end up back where you started, or you start an isopleth on the edge of the map and you continue until you reach another edge of the map. The other thing that people are tempted to do is they're often tempted to draw isopleths in areas where there's no data. And I would like to caution against that because we just don't have any information, and if you have preconceived ideas about what the weather is actually like in those regions, it may be wrong because it's not based upon anything in reality. And those isopleths, as I said, should continue to either the edge of the paper or the edge of the data, unless, of course, it forms that complete circle. And the thing about isopleths is they have to have values that are higher on one side and values that are lower on the other for the entire length of the isopleth. And as before, when it comes to units, you need to label your isopleths. If you don't label an isopleth, it really doesn't mean that much. And when you're done, it should be visually appealing. You should be able to quickly look at it and identify the regions of high values, the regions of low values, and the gradients. And those gradients are really important in determining the location of fronts and determining where the wind speeds are going to be strongest, and a lot of where the weather action is happening along those gradients. So here's an example from the Weather Channel of a surface-based weather map, and it's got some problems associated with it. Hopefully you can identify what those might be. But we have high pressures and low pressures that have been identified. We have these lines that are circling the high and going around the low. Those are going to be isobars, lines of constant pressure, but they are not labeled, obviously. And then they have their lines are extending out over the oceans where we likely have no data at all. So the other thing that I can see on this is that they have also identified locations where you have weather fronts, and those fronts are going to be temperature fronts, and the isobars, the lines of constant pressure, are not the best place to identify the weather fronts. You can identify a trough coming from the low that is up in Canada, and that's a likely location of a front, but you really need to look at the temperature in order to see exactly what's going on in those locations. So if we want to contour sea level pressure, it's really common to have closed loops near the centers of high and low pressures. The standard convention for contouring sea level pressure is that we do it for isobars usually every 4 millibars, and we center it at 1,000 millibars or 100 kilopascals. So you do 100 kilopascals and 100.4 and 100.8 and 99.6 and 99.2 kilopascals. And on the right, we have a low pressure zone that has been contoured, and you can see that that low pressure zone has a trough associated with it, and that trough happens to be the location of the surface-based front that is associated with that particular low pressure zone. If you want to get some practice contouring, Steve Ackerman and Tom Whitaker at the University of Madison have put together a really nice contour analysis tutorial that's interactive. And you can visit this website. I checked to make sure that it was still active, and it is. And you can go through and it will walk you through the process of doing some linear interpolation and trying to identify, where the contour should go. And then once you have use the contour analysis to identify weather fronts, then we have different symbols that we can use to describe those. So on the top there, we have a warm front, which is red with these semicircles on it. And the semicircles are always located on the side of the front that shows which direction the front is moving. So this particular warm front is moving from the bottom of the page to the top of the page. We do the same thing with the cold fronts. The cold fronts are blue, except for they have these triangles. I like to think of it as biting cold, and that these are the teeth on a jack-o'-lantern. And then we have a stationary front. A stationary front is not moving north or south. It's stationary. And so you have cold air typically that wants to move south in the northern hemisphere and warm air that wants to move north. And when they collide and don't move, you get a stationary front. There is such a thing as an occluded front, which we will talk about more in the coming days. And then you can have fronts that are aloft, that don't reach down to the surface. And you can identify those with these open values. And then we can also have a dry line, which is a front based not upon temperature, but is based upon humidity. And then we can also identify the axis of the trough associated with the pressure values. And we can also identify the ridges associated with the pressures or the heights.